everyone. My name is Annie Polish. I'm a third-year PhD student at Harvard University, working with the BICEP3 collaboration, and today I'm going to be telling you about upgrades to the rotating polarized source for calibrating BICEP3. So the BICEP3 telescope is a 95 gigahertz small aperture polarimeter designed to search for primordial gravitational waves, or B modes, in the cosmic microwave background, and it's physically located, as you can see, at the South Pole. So I'm going to go pretty quickly through this section because I assume that most of you are far more expert on this subject than I am, but essentially there are beyond the standard model theories that predict parity violations in electromagnetism, and that would potentially manifest as free space itself being slightly birefringent. And the cosmic microwave background is a great tool for probing that because it gets us the largest possible line of sight to integrate over and build up polarization rotation. And we have this CMB polarimeter, which should be able to detect cosmic birefringence if it exists. But the problem is that for our typical CMB observations, we do only a relative polarization calibration in which we basically assume that the cosmic birefringence angle is 0. And this is not possible to get out of purely in analysis because the cosmic birefringence angle is fully degenerate with the instrument polarization angle. So to become sensitive to cosmic birefringence, we need an external absolute polarization calibration to reference our detector's polarization directly to gravity. And that's what we aim for with this rotating polarized source. So here's an image of the RPS itself. It consists of this amplified thermal noise source, which has inherent polarization on its own, but then we clean up and define with a mechanical reference the polarization of this source with a wire grid polarizer, which is located on the front here behind this plastic cover. Then the whole RF assembly can rotate within this rotation stage, and then the base plate that everything is tied to is referred to gravity with this precision tilt meter. And there's a number of calibration steps involved in this. We have to collimate the horn axis to align with the rotation axis of the stage so that we're actually just rotating the polarization and not nutating around some other axis. The tilt meter has to be calibrated to gravity, and then the wire grid is mechanically calibrated within the rest of the assembly so that when the whole thing is rigidly assembled, the wires in the wire grid are directly referred to gravity. And we check our work on our calibration using this instrument shown here, which we call the in situ absolute angle calibrator, or ISAC, and it consists of another wire grid and another precision tilt meter with a very simple detector diode receiver, and we can go through all the same calibration procedures on the ISAC and wind up with a absolute angle reference that we can check the RPS against. So for calibrating BICEP3, we first have to essentially flip BICEP3 over onto the horizon with this big mirror. Typically, it cannot observe very low angles near the horizon. Then we put the RPS up on our calibration mast at a range of around 200 meters so that we're in the far field. And the RPS, when it sits on this mast, it's in this environmental enclosure box, and it has these red alignment strips that you might be able to see in this image that we use with a zoom lens to visually align the RPS pointing with BICEP3. Then the primary data type that we take during these measurement campaigns is a modulation curve. So what we do is we rotate the RPS in 30-degree increments through its polarization angles, and at each rotation increment, we raster the telescope across the source. So that gets us, for each detector, how it sees the source as a function of the source's polarization angle. And then we fit a model to the measured source amplitude as a function of the source's polarization angle, and that gets us the detector polarization angle with respect to the RPS and thus with respect to gravity. There's one hiccup here, which is that we have this source with a well-known polarization referred to gravity. We have a telescope with well-measured per detector pointing. We know where a given detector ends up on the sky. The only catch is that we just put a mirror in between, and in general, we don't know what the mirror is doing. The set of all of the beam centers should move as a whole across the sky. We allow translation and rotation, and we fit for the overall translation and rotation of all of the beam centers together. And this is typically cross-checked with observations of the moon. But once we've done this, we actually do have the ability to directly reference the detector polarization angle to gravity via the RPS. And we've done this before. We've done a number of previous measurement campaigns. I'm going to talk about our most recent one. These are plots that are from a paper that we just put out on the archive that is referenced in these figures. So the RPS is already telling us new information about our detectors. So here I'm showing the whole focal plane of our telescope, which is made up of individual detector tiles, which are a physical module with detectors and biasing and readout equipment, and each of these tiles is then installed into our focal plane. And you can see that, as we would have predicted, the tiles have some overall clocking relative to each other. This is consistent with some tiles being installed at a slightly different angle from the other ones. And when we subtract off the median angle for each tile, we can see smaller variations within the tiles. This is probably showing evidence of slight manufacturing defects. But this is new information that we would not have been able to gather without the RPS's help, and it is a good demonstration of the precision and repeatability of this instrument. But when we went to go and write up our actual cosmic birefringence constraint, we ran a bunch of bench tests to directly measure the impact of various known setup uncertainties on our polarization angle. So I was talking before about the alignment of the RPS in its pointing using these alignment strips, and we think we got it pointed correctly to within about a degree. So we set up the ISIC as a receiver and the RPS as our instrument under test on the bench so that we could rotate the RPS in azimuth and directly measure its impact on the polarization angle. And unfortunately, what we found is that the polarization angle reported by this measurement differs by several tenths of a degree with around a degree of azimuthal misalignment. This dominates our error budget. This is in fact larger than the total error budget we were aiming for, and because of this, we decided not to unblind in this paper. We go through all of the analysis that would be required to get to a cosmic birefringence angle, but ultimately do not look at real telescope data because this error was so glaring and we believe we'll be able to fix it. So the rest of this talk will be on how we tried to fix it. And there were a whole range of things that we tried that did not work to fix it. I'm only going to go through one of them here because it's an additional upgrade that we added. So working with an undergrad that I was supervising, we added a very precise absolute encoder to the RPS, and this simplifies our mechanical error budget by a lot because it means that we directly refer the wire grid, which is in here, to the whole moving assembly of the RPS, and then through the absolute encoder to the base plate, which again, sorry. Yes. With this absolute encoder, we can refer the wire grid, which is rigidly mounted in the shroud here, through the absolute encoder to the base plate, which is carrying a tilt meter, which references the whole thing to gravity. And Kane also added automation to our azimuth tests, which allowed us to do more precise and repeatable tests for tracking down this error. So the rest of this talk, again, will be on what this error is and how we've fixed it. So here is the basic type of plot that I'm going to be showing for the next couple of slides. This may look slightly like a modulation curve, but in fact, this plot contains 27 modulation curves. Every individual point on this plot is an entire modulation curve. So what we do is we send the RPS to a given azimuth angle on the x-axis and elevation, which are the different traces, and at that location, we take a modulation curve, fit for the polarization angle, and that's what I'm plotting on here. And we can see that there's a few tenths of a degree difference with a degree or two of azimuth change. And we tried a whole range of things to get this to go away, including a wide range of perturbations to the bench setup. We were initially very suspicious of this close-range bench setup and ultimately convinced ourselves that it was a valid test. But the thing that first made progress on this was that we replaced the horn that we were transmitting through, which was a 15 dBi standard gain pyramidal horn, with another, also 15 dBi, also pyramidal horn. And it looks like our azimuth dependence has flattened out by a lot. However, this was not really an apples-to-apples comparison because the new horn that we got was 5 or 6 millimeters longer than the original horn that we were using. And so the aperture of the horn was significantly closer to the wire grid. So I added some spacers to move the wire grid farther away from this new horn to get it to the same distance as the previous one, and the azimuth dependence effects returned. So, believing that this was a crucial variable here, I tested an extreme scenario where we had the horn attached via 3 inches of waveguide to the source box, and I took out all of that waveguide and mounted the horn directly on the source box. And we can see roughly the same, qualitatively, this is the same morphology. We've got this sort of, we've got this, these sorts of curves, and it flips sine as we change in elevation, but this is an order of magnitude more intense. These are full degrees. So clearly the horn to grid spacing is very important here. I wanted to see what the beam of the RPS looks like when we're in this scenario. So here I'm measuring the copole beam of the RPS. The orange trace is with the shroud removed, so I'm just measuring the copole beam of the horn, and it is in fact a nice Gaussian. And then with the horn all the way back and the shroud installed, we get this crazy trace in blue. And the key here that that sort of cracked this problem open for us was that the spacing of these peaks, which are roughly 2.5 degrees away from zero, corresponds with 1.22 lambda over d to a characteristic length of about 85 millimeters. And the inner diameter of the wire grid that we're using is 88 millimeters. So what we think is going on here is that the horn is unintentionally illuminating the conductive aperture of the wire grid, and that is diffracting, re-radiating, producing its own beam that interferes with the Gaussian beam from the direct line of sight from the horn, and that produces these ripples. And because it's a conductive aperture, that's also responsible for the polarization effects. And I just want to point out that even though this the plot that I just showed was a very extreme scenario, we've also seen these ripples in the actual measured beam of the RPS in the state that it deployed in. And yeah, we've seen these ripples in the beam of the RPS in the state that it actually deployed in. So this effect is present, and it is very much possible that it is responsible for the polarization errors that we're seeing. So with the knowledge that the illumination of the wire grid's aperture was the key problem here, we added a number of pieces of absorber inside and outside of the shroud to try to intercept any lines of sight between the horn aperture and the wire grid aperture, so that the only thing we're seeing should be the primary Gaussian beam from the horn. And this resulted in an azimuth dependence in our polarization that is of order a few hundredths of a degree rather than a few tenths, and is in the neighborhood of the modeled alignment error of 0.035 degrees that we were hoping for in the initial modeling of our birefringence measurement capabilities. So we are very optimistic that this instrument will be able to deliver the precision and accuracy that we need to be able to take this measurement. So in summary, we've found that the few tenths of a degree azimuth-dependent polarization error is a real property of the RPS beam. It was not an artifact of the bench tests, and that means that it was present in previous years' RPS data with BICEP3. This error is caused by the RPS horn illuminating the conductive aperture of the shroud and the wire grid, and mitigated by reducing that illumination with either or both of moving the horn forward and adding absorber within the shroud. I also think it's important to point out that this error was not predicted by any of our models. We only found this because we decided to do rigorous and empirical testing with this bench setup while building our error budget. And we think that that's very important to do on these sorts of precision measurements. And the upgraded RPS with all of the changes that I've described is at the South Pole right now and preparing for another measurement campaign as we speak. So stay tuned. All right, thank you everyone for listening. And I'd especially like to thank Clara Vergas and James Cornelison, with whom I worked very closely on this project. So thank you all.